Graph Theory Class 7 Video 2. In this video we're going to continue talking about planar graphs, and in particular we're going to talk about faces, edges and vertices. So let's begin with a definition. Given a drawing of a planar graph without edge crossings, so it's always possible by definition to draw a planar graph without edge crossings. So if you have a drawing of a planar graph without edge crossings, we define the following numbers. So we let V be the number of vertices, E be the number of edges, and F be the number of faces. And faces is the new thing, okay? A face is just something enclosed by vertices and edges. So really simple, this graph right here, okay, has one face right here. So I'll call this face 1. Has another face right there, face 2, and you always count the outside as a face. So the whole of the outside is a face as well. So for this particular graph, we have f equals 3. There are 3 faces. And we also have the v equals 1, 2, 3, 4, and e equals 1, 2, 3, 4, 5 for this particular graph. So let's do some more complex examples. Calculate V, E, and F for the following graphs. Okay, so if I start with this graph right here, okay, well, V is very simple, it's 4. E is also quite simple. There are 4 around the edge and then 2 diagonal, so that's 6. Now F is the only sort of confusing one. So before you can calculate the number of faces, you need to go back to this definition and realize it says given a drawing of the planar graph without edge crossings. But this drawing has an edge crossing, right? This particular drawing has an edge crossing. So before I can calculate F, I need to redraw this graph without that edge crossing, and I can redraw it like this. This is perfectly fine. And now I can count how many faces. I see 1 face, 2 face, 3 face, 4 face. So it's 4, 6, 4, like this. Okay? It's really important that before you can count the number of faces, you need to redraw it with no edge crossings. Okay? I can do an example that looks a bit like this. So if I draw something like this, okay, then V is equal to 6, E is equal to 6, and F in this case, well, there's a face on the interior and there's a face for the whole of the outside. But that's it. There are just 2 faces. Okay, just 2 faces. And because it's already planar, because it's already drawn without edge crossings, I didn't need to redraw it. Okay, let's do another example. So this time, why don't we try this graph from last time? Okay, so right now there's lots of edge crossings. So I can't calculate the number of faces using this particular drawing. I have to redraw it first so that it doesn't have edge crossings. So I redraw it like this. Now I can calculate the number of faces. So let's just begin with the vertices. I see 6 vertices. Edges, I see 8. And faces, I see F1, F2, F3, F4. So I see 4 faces, like this. Okay? And this is how you calculate the number of vertices, edges, and faces. So I want to now talk about a theorem involving these numbers, involving V, E, and F. And this is a very important theorem. and it's kind of a cool theorem as well. Okay, it's called Euler's formula. Same Euler who has Eulerian graphs and Eulerization. This same Euler has a formula, and it says if G, if a graph G is a connected planar graph, with V vertices, E edges, and F faces, then these numbers satisfy an equation, and that equation is V minus E plus F equals 2. And this is always true, no matter what planar graph you choose. Okay, so there are infinitely many planar graphs out there, and there are infinitely many ways of drawing them, but no matter how you draw them, if you add up V minus E plus F, you will always get 2. Okay, why 2? Yeah, it's a reasonable question to ask, where the hell did this number 2 come from? Well, that's kind of like a deep question, and it's sort of just magic for now. Okay, so I just want to quickly show you this in action. So if we go back up to our example, we have 4 minus 6 plus 4 is 2, so this checks out. 6 minus 6 plus 2 is 2, so this checks out. And this one here, 6 minus 8 plus 4 is also 2. So our 3 examples right here, you know, as expected, none of them are a counterexample to this theorem. Okay, I'm not going to go over the proof of this theorem because it's a bit complex, but it's a cool theorem to know. Okay, this is Euler's formula. That's the end of this video.